Just because like she probably got 90.
Yeah, I'll say that. 90 or above.
Okay, so this week seems 4 chapters. Chapter 16, 17, 18, and 19. Chapter 16 is relatively easy. A very short chapter. 17 a little longer. And chapter 18 again is a short one. Chapter 19 is going to be long, very long, probably the longest one. Chapter 19, you can see a lot of reactions. So let's first start on the chapter 16. As you know, tomorrow we will have our second exam. And the second exam will be on the 4 chapters, right? 12, 13, 14, 15. You just started the lecture notes and the homework. So you know what to study, you just have to study. And I think you pretty much just memorize those reactions. Any questions? Yeah.
I was wondering, because I did some homework this weekend, and there were so many. Should be open to like open notes. There's so many.
You know, there's a lot of reactions.
What if we only have 45 minutes for the exam instead of an hour?
Okay, so now let's continue on to chapter 16. Chapter 16 about ethers. So as I said, if you have some of those difficulty remember those equation reactions, try to memorize them by abrogatives. So at the beginning of each chapter, let notice you see the abrogatives. If you see the chemical reaction of ether, and you think about what are the few reactions of ether. If you memorize in your mind, you can skip those reactions. If you think that ether has 3 reactions, and 1 reaction you don't know, then you go back to read the lecture notes again. So you go through a few times, you get less and less. I mean, you get less and less, you have to go back to read the lecture notes. And then, when you pretty much by tomorrow, you only have like 2 or 3, don't remember, then you're pretty much ready. We studied this chapter about ether, epoxide, and sulfide. First, talk about naming, and obviously there will be some naming. And the functional group class names list both alkyl group in alphabetical order and add ether at the end. When both alkyl are the same, we use the prefix di precedence the name of the alkyl group or alkyl group. Then there's another way of naming, substitute IUPAC name, which means you find out the longest chain is the parent, and then override is named as alkoxy. Let's see some examples. Right. So one example is this. I have, you know this, we use this in the lecture. Right? And this is the functional group name will be the di-S or ether. Di-S or ether. If you want to name this as the substitutive IUPAC name, you should name this as epoxy acid. So you name one of this left part or right part the same, epoxy and acid. Right. Second example is this. So obviously this, you can see the S or meth or ether. Alphabetical order, S or comes first. S or, and then meth or ether. Substitutive inorganic name. You find the longest chain. The longest chain has 2 carbons. So therefore, this right side is methoxy. Methoxy. And then you add this as a substitution name. So it will be acid. Methoxy acid. Depending on what you memorize, so on the test, and you can use either one. And let's see this one. Three carbon on the right. And then we have this chlorine. Okay, so you're going to name this alphabetical order, and you in like the functional group naming, you first name that 3 chloro. Propyl, and then S or okay. I will add the name here, right? And then ether. So this is sort of the functional group naming. You just remember there is an ether and an. Right? Substitutive naming, and you should name this as the longest chain with 3 carbon, right? And then you have on this 3 carbon, this 3 carbon, and there's Cl, and there's other this epoxide. So this Cl here, and this epoxide here. That's 3 carbon. Okay? So then we should add, you start the numbering. Well, I think that. And when adding started the naming, so that's a little like a priority. Okay? So I think somewhere I will show you in the lecture notes the priority of those functional group. Halogen has the lowest priority. The second priority is those ether or epoxy. Then you have those alkene. Single bond or single bond. Then you have all the double bond, okay? And then you have the then you have the triple bond. Then you have the double bond, and so on. So in this example, you have this. You are going to name this on this side. Okay? You are going to name this 1, 2, and 3. Understand? Okay? So this answer has a little high priority than the chlorine. Chlorine and halogens. Halogen is at lowest. The lowest priority. So therefore this naming, you numbering like this, but you put those alphabetical order still. Okay? So this will be our chloropropyl. Let's start with C. So we'll see 3 chloropropyl, and then name 1. Name 1. Deoxy propane. So you just name this as some of those alkene or single bond. If other functional groups are present, the ether part is considered as an alkoxy substituent. You already see that example. And let's see this. Example here. I think what we should name this. PR here, and if I have this mesoscale here, according to what we said, we shall name this as, so again here you have a pi, you break the pi by use, the ether has different high priority, so this will be 1, 2, 3, 4, and 5. And 5 means we will have this painting. And then you just list those substituting alphabetically. Okay. So bromine will come first, therefore you have 4 bromo, and then 2, I don't know how to space, I write the pentane first. Mesoscale, I just put this in and then. Alright, similarly, let's see this, there's another pi here. So mesoscale and epoxy. Right? So both of this substituent is some of those alkoxy. Okay? What you name, you can like the E come before the M. So name this 1, 2, 3, 4, and 5. So therefore you will have these 2 epoxy and 4 mesoscale, and you still have the pentane. So this chapter is about ethers. Ether, that means you have this oxygen atom single bond to 2 carbon atoms, to some other carbon atoms. So therefore you can see sometimes the oxygen can bond in two other carbons in a cyclic structure. And that's therefore you will have this oxygen, which is a very, very important epoxy you are going to study in this chapter. Example of this is you have a 3-member ring, 2 carbon, 1 oxygen, and we call this oxy ring. I will tell you the pattern to memorize this for you. Okay? And so there's it's also called the ethylene oxide. Ethylene oxide. Next one, you will have 4-member ring, but you will have 3 carbons. And this guy called that oxytane. Next one, we will have 5-member ring, 4 carbons, 1 oxygen. And this we call oxonate. Then the last one will be the 6-member ring, which means it has 5 carbon, 1 O, and this is simply called the oxane. Okay, now the last 2 also have some of those common names. This is called tetrahydropyrene. And this 5-member ring called the tetrahydrofurane. Okay, now the pattern to memorize is you don't really have to memorize it, you just wonder. So all of them have this part. So OX and then A and E. So when in the middle, for the 3-member for the oxygen is so this guy, let me change like the pen, and you will see the You'll need that. Minimize that. So what is the pattern is for this guy you have the IR. For this guy you have the ET in the middle. And for this one you have OL in the middle. For this one there's nothing. Nothing in the middle. Alright. Now sometimes you will see those diethers or polyethers, and you see those polyether diethers mainly as like those simple ethers you just use as a solvent, and those solvents if you have diethers, their boiling point is very high. Okay, one example of diethers is this. Okay, so now if you want to name this as a substituent name, and you will name this as 2-dimethoxy acid. So therefore this is 1,2-dimethoxy. Okay. That means the left side, right side has 2-methoxy. And then the middle has 2 carbon. So therefore 2 carbon means acid. Okay. And you also have a diether in a cyclic structure. In cyclic structure, like this. This is so what we call this is 1,4-dioxane. Last one, and it's called the dipyramide. Remember we use that in like the in the Wolff-Kirchner reduction. There's O. So this is O. Diethylene, glycodimethyl ether. You will see this diethylene. So this is ethylene, this is ethylene, this is ethylene. Diethylene, if glycol, these 2 guys on the end of this 2O should be OH. But now you have a dimethyl. Okay. And then I will roll up a little bit, I will put this ether here at the end. So you know sulfide and oxygen in the same group of 6A. Okay? So the sulfide is analog of alkoxy group are called the alkyl group. The sulfide analog of ether is named the same way as ether, except the sulfide is used instead of the ether. Let's see 2 examples of sulfide. And this we call that diethyl sulfide. Diethyl sulfide. If you want to name this as a substitutive, I will pick a name. It will be ethyl acid. Another example is this. And this will be cyclopentyl sulfide. Cyclopentyl. And then methyl want to name this as a substituent. Substitutive name. It you find the longest chain like 5-member cyclopentane, and your substituent will be this meth or thiol. Cyclopentane. Vice versa, if I give the name, you should be able to write out the structure. Okay? And here are 3 examples in the problem 16.1. The first is the chloromethyl methyl ether. So that's the functional group name. Okay? Chloromethyl, which means you will have this Cl and Ca2. And the other one is simply metal. So there will be O, and then you write out the functional group like this. And this will be Ca3. The second one is the 2-chloromethyl oxygen. Oxygen, remember, is this 3-member ring like this. The number is this is 1, this is 2, this is 3. Whether you name the left one is 2 or the right one is 2 doesn't matter, right? So then the other substituent is chloromethyl again. Chloromethyl should be CH2Cl, and you want to bond into the one of this carbon on the oxygen. So therefore you have the structure like this. And this is the same. If you write the line structures as this. Then epoxide, like this oxygen, you can name that by adding the prefix epoxy to the alkane name of the parent compound, specifically specify the number of those atoms to which the oxygen is attached. Okay? Let's see, one example is we see this. This epoxide usually come from the alkene, the double bond. So let's say this we call that 1-butene. If you have a structure like this, and adding this epoxide, and again epoxy has lower priority. So when you number this, you will number this is 1, 2, 3, 4 carbon, and your epoxy is on the 3, 4 carbon. So therefore you will have this is 3 and 4 epoxy. Then you indicating where is the location of the double bond on the first carbon. Okay. 1 and butene. You only need one number to indicate the double bond on the triple bond. Right? You don't have to see. So here just one number. You don't see 1, 2 butene. To indicating the double bond on the triple bond, you just indicating the first carbon. Don't number in the name. Don't call something like 1, 2 butene. So one number will be enough. Even though you have 2 carbon in the double bond. Okay, any questions? Okay, the second objective of this chapter is structure and bonding. These are very similar to water and alcohol. Epoxide have a lot of angular strain and react to release this strain, opening the ring by breaking a CO bond. You see the angular strain in this oxide ring. And so this bond length, 147 picometer. The bond length here, between carbon O is 144 picometer. And the bond angle, so that's the bond angle COC. So it's so the bond angle here, bond angle here is 61.5. And the other bond angle here is a little less, 59.2. If you want to exaggerate the structure of the oxide ring, it sure looks like this. But this obviously is exaggeration. It's kind of flat. Physical properties. So the physical property, which means you think about the boiling point, melting point, solubility in water. Because you have the oxygen in the ether, so therefore it can be the hydrogen bonding acceptor. With ether, for example, the diethyl ether, right? And we have two lone pair on oxygen. If you have water, like nearby, and water has an H, so therefore you have the so-called this bond, hydrogen bonding. So this bond here is a hydrogen bonding. Hydrogen bonding is a very strong intermolecular process. So therefore, ether is actually like the diethyl ether, solubility in water, not that much. Pretty much about 1 ml solubility in water. In H2O is 1 ml in 10 ml H2O at 25 degrees Celsius. So when we extracting those organic compounds with ethers, actually we lost about 10%, and it's about 10% of those compounds. So sounds like for every 1 ml, for every 10 ml ether we use, and you lost like about 1 ml in water. So alcohol and water can also hydrogen bond into themselves. If you have alcohol, let's say one alcohol is this 1 butanol. So you have those long pairs, and if you have another 1 butanol nearby, long pairs. Now you have this hydrogen bonding, called H bonding between these two alcohols. And that will make the boiling point of alcohol much higher than the ether. Ether can hydrogen bond into water, but cannot hydrogen bond into themselves. Right? Let's say you have a diethyl ether. Long pair here, okay? And you have another diethyl ether right here. You don't have you have some of those H here. I said there's an H here, but this H cannot hydrogen bond into this. Okay? So this cannot happen because that H is not bonding to a very electronegative atom. It's bonding to this here, no hydrogen bonding. hydrogen bonding between two ether molecules, the bonding point is like lower than those alcohols, because alcohol can hydrogen bond themselves. You can see this in the table, right? So as we already draw that before for this one, ether cannot hydrogen bond to themselves, but ether can bond to the water. So if you have this again, and it can bond to water. The water here. So this H and then this O can hydrogen bonding. So this is the H bonding. But it is between ether and water, not between ether and ether. Okay. Another type of ether called the crown ether. So crown ether, well, even some of those simple ether, has a very special property. Okay? That means they can complex with some of those metal ions. Okay? Especially some of those transition metal ions. They have a lot of they have a lot of those empty orbitals, d orbitals. But even with those small ions, because ion, that means you take some of those electron away. So anyhow, you have some of those empty orbital. But those, for example, potassium ion, you take the electron away, you will take the electron away from those s orbitals, and there is only one s orbital. So your complex probably will be limited by compared with those transition metals. Transition metal has a lot of those empty d orbitals. The d orbital have 5, so therefore you can accept more electron from the crown ether. But here I show you this potassium. Maybe not a good example, but anyhow it can happen, right? So you can see the complex, for example, is R2O ether. We call that is our Lewis base, and M plus, which means the cation. Okay? So here is our cation. It can complex with our ether. The electron flow is indicated by the red arrow, and you produce this complex. So this complex here. This complex here. And this is also the reason. I think one of the reasons we usually use those ether in the grignard. We will also have that experiment. So when we do the grignard experiment on labs, we will take, for example, bromo benzene, and then we will put some of those magnesium metal, and so then we will produce the grignard. And the diethyl ether is a very good solvent because you produce the grignard, and the grignard is kind of ionic, but you still have the Mg, the metal, and then this complex will increase the solubility of your grignard. Right? So when you have ether or crown ether, and crown ether, that means you have a poly ether. Okay? Poly ether, that means you have a lot of those oxygen and carbon bonds like those, and then you produce a cyclic structure, the crown ether. So then what will be in the middle to produce a complex is not those negative ions. For example, if you have potassium fluoride, And you will see that pretty much you can dissolve into the chrome ethers is because the chrome ether will take in the positive ion, put in the meter, and here is not the fluoride, not the negative ion. That makes sense, right? Because in the meter of the chrome ether, there is a lot of oxygen. Oxygen has a lot of those long pair of electrons, right? So you kind of relatively negative here, and you cannot put a negative here, but negative repair.
So it takes the positive cation.
Canons, yeah.
So the ion can come in reaction with like the bromide.
Very good, very good. That's the next example. Okay. Next example, we know the so-called nuclear facility. That means which one is the very better nucleophile. So usually the better nucleophile, like the better one is the iodine. Iodine is the better nucleophile. Iodine. So those nucleophile ability, I1 negative is better than the Br1 negative. That is better than the chloride. Usually, that is much better than the fluoride. The reason for that is those acid strengths. So the HI is a stronger acid than the HBr. That means your base become weaker and weaker. So usually the H will bond to the fluoride F1 negative very strongly. But if you use a chrome ether, and you can take that usually those positive ion that usually attach on the fluoride, as what Maria said, you take that away, then you left over the fluoride ion kind of displaces, that are floating around in the solvent. So therefore you will have this reaction happens, and it's kind of strange. Usually you will not see the fluorine will replace the bromine. This can happen. And now you replace the Br by X. And notice what you use. You use 18 chrome 6. 18 chrome 6 is this chrome ether there. So this is the name of cysteine. 18 means you have 18 atoms in the ring. 6 means you have 6 oxygens. So 18 chrome 6. That is our usual pattern study of organic chemistry. That's a good idea to use a flashcard and whatever you want to memorize. Then you also find a little pattern. For each chapter, we pretty much have the same pattern. Each chapter will start with nomenclature a little bit, physical property, the structure, and then we'll study how to prepare some of those what we study. If we study alcohol, we'll see how you prepare alcohol. If we study acid, we'll see how you prepare acid, nitrile, aldehyde, ketones. So some of those patterns, then you will see what are the reactions for those compounds. So now let's see what is the way to prepare the ethers. Any questions? We're going to see like 3 common ways to prepare ethers. So right now we will just concentrate on the ether of alkyl ethers, and we will leave that ether that has one part you have the ether means you have O and O. Okay? And right now we will study those air pure here and also air pure here. Okay? So later on,
Right there where it says the bromine, and you say we have to use a weaker acid, you said? For like the KF, for the solvents
K-
and the catalyst. Right, so we have bromine, we have to use, you said, a weaker acid?
I said the weak acid compare with HI.
Oh,
So therefore the BR is a little stronger, stronger base. And so those base, whether they are stronger or weaker, also influence their ability to be a nucleophile. And so let's see the fluoride and the HF is a very weak acid. So that makes the fluoride a very strong base. So therefore you probably don't see like too much of the F1 negative and free F1 negative ion most of the time, right? They will combine with the H. And once they combine with the H, you lost the long tail of electron, you lost the negative charge on it.
so we use a strong base, is what you're saying. Instead, the KF.
Well, the nuclear fire ability and base ability is kind of a complex issue. So for these halogens, so HI is a stronger acid, so therefore make this I1 negative is a weaker base.
So for, like, if we were using iodine or chlorine, you could also use that base. You could use the.
Yeah. If here, this BR here, so then we do like this problem. If you here BR can be replaced, you can replace this BR by I and by CL. And then if you use the chrome ether, if you don't use the chrome ether, just simply take it as a sodium fluoride. If you here is BR and you don't use the chrome ether, simply take a sodium fluoride. And the sodium chloride may be in acetone or in alcohol as a solvent because you have to dissolve this guy. Right? And then this reaction will not happen. If you simply use like this, platinum chloride is never here. Right? If you don't use this to take the platinum ion away, right? And then this platinum ion will always together very close to this fluoride. And that will blocking the fluoride ability to attack this carbon here. Alright, so now let's see the three ways of prepare ethers. Okay. One way is just simply acid catalyze the condensation of the primary alcohol. It works best with primary alcohol. So when you demo here, and you produce this, you can produce this dibutyl ether simply by, I need to move this, let's say doing the other way. So how you prepare this, what are the reactants? And you can simply take those, simply take this one butanol. So you take two of these, then you just adding a little bit of acid, for example, H2SO4, and then heat. So you kind of dehydrate the alcohol. Yeah, you need two of the alcohol, right? Because you see in the ether, we have two of those carbon chain. Right? You take one of those 4 carbon, and 4 carbon on left side, 4 carbon on right side, and then you have the oxygen in the middle. So that is the ether. I remember some of those traditional way to sometimes like kill the pain. So you have like a stomach pain. I saw some people just get some of those alcohol, maybe like vodka, maybe some of those rum, and then they will take like 1 cup of that and put that on fire. You can just take a match, put on fire. So after some time, after the alcohol burn for some time, then you drink that, and you sometimes will stop the stomach pain. So I thought what's the reason for that? I think for one reason is that you heat up the alcohol, dehydrate, and you produce ether. I think ether in like before World War II is used for those anesthetic. To put on some of the wound, and that will stop the pain. Okay. Now this method, it works only works with the primary alcohol. If you take some of those secondary alcohol, you know that in like that last chapter, chapter 15. And it mainly goes through the elimination reaction. For example, if you take some of those secondary alcohol, if you don't use 1-butanol, you use 2-butanol, and you use H2SO4 and some heat. What you produce is those elimination reaction products. You will produce a mixture of that. You might produce 1-butane, or you will produce trans 2-butane, or you will produce cis 2-butane. The next way to prepare ether, okay, is use like the electrophilic addition of alcohol to alkene. Alkene are those double bonds. So you somewhere have a double bond in your structure. Okay? And then you can use the acid catalyzed. So acid catalyzed, let's see one example. This 2-methyl 1-propane. You don't have to see 1, but there's only 1 possible location. So this is 2-methyl propane. You add CH3OH. And some of those acids are the catalyst. And you produce this tubular methyl ether. Now this next problem 16.5, you will see the mechanism. So how can we take alkene double bond? And we were adding some of those epoxides on one of these carbon that in the double bond. Okay, you know the double bond has like an electron on the in those vicinity. Okay, the kind of electron bridge. Okay. So some of those electrophiles were looking for the double bond. So again, I hope you will, if I give you the name of the step, and you'll be able to draw the electron flow. So the first step, you need to mechanism produces terbutyl metal ether from this 2-metal propane with methanol with acid as a catalyst. Is protonation of the carbon-carbon double bond, leading to the more stable carbon cation. Okay? If you start with this double bond here, okay, and you have acid, just simply use H plus as acid. Okay. But depending on what is your solvent, so this H plus, maybe on H2O, or it is on the alcohol. So in our example, we just have alcohol. So if you want to see explicitly where this H plus comes from, H plus comes from sulfuric acid, for example, and then actually, really like in the reactions, you will see this H plus is actually on this methanol. Okay. But for simplicity, you can just use H plus. And this will be our electrophile. Okay. So this H plus is our electrophile. Okay. So therefore the electron will flow onto it. Then we have a choice. Okay. So we will take like the electron wave and use it bonding to the H. Right? So then you will have a positive charge. Your positive charge has to balance. You have right now you have one positive charge on the left side. Your charge always balance too. Just like you balance the mass. Right? Right now I have one plus on the left side, and where will be our plus on the right side? On carbon. On which carbon? On the central carbon. Okay? The central carbon right here. Right? So this will be our tertiary carbon cation. And particularly for the name terbutyl cation. Now the second step, we'll see some of those nucleophile will come in. And now you have a positive charge. Positive charge, yeah.
Why is that methyl to have a percent hydrogen?
Why the 2-methyl group? What do you mean the 2-methyl?
Like on the turbulent side,
Mm-hmm.
why does the H, why are there 2 H's instead of the methyl group?
This one here? Oh no, this one is our acid. Yeah. So we talk about when we see the acid catalyzed. Also, where is the acid? Sorry about this because I usually just think about you have acid H2SO4, right? And that's a very strong acid. So they were usually like ionized. So we'll give you the H plus and then HSO4 one negative. So then this H plus usually not by itself. So usually this H plus will be on some of the solvent, depending on the solvent. Okay, now the name of the second step is methanol acts as a nucleophile to capture the terbutyl cation. So terbutyl cation becomes very, very a good electrophile. So you will see some of those, you will attack some of those nucleophiles. Nucleophile, which means has some of those, either have those long pairs or negative ions. Right? We talk about the nucleophile ability like those bromide iodide, right? And vicinal is not a very good nucleophile because that's a neutral molecular. It's much weaker compared with those nitrogen or some of those bromide, iodide. But right now you have this very good like electrophile, this cation. So now the cation, the terbutyl cation, and the plus is O, H. And you know the electron flow go from the lone pair or double bond onto some of those positive charge or single bonds. So that will give you the intermediate. That will be your conjugate acid of your ether. So you almost get an ether, but right now you have the H plus on the oxygen. So what will happen next? So if right now you have this conjugate acid of the ether, and you want to get an ether, so sometimes the mechanism it will help you to go.
Is that water or is it
Oh, that's a good question. So there's not water, so this was methanol. Okay, thank you. All right. Any questions? Go around the line with timing. If you use water, what you will produce? If you don't use methanol, that means your solvent or your reactant is not methanol, but you use water with H2SO4. What you will produce?
water acid?
So therefore, this one will become H, right? It will become H. Now, what will happen? You will think about what will happen next step, right? Next step is sort of the deprotonation. Right? So either here is this methyl or H, right? And you will see the two main. Very good, alcohol. Well, these are the sort of one of the products, Markov-Nikov product, right? So first add H plus onto those carbon has more H than the OH, or go to the carbon that has less H. Similar. So if you're adding alcohol, right? The alcohol will also go to that carbon that is more substituted, okay? Or the carbon that has less H on it. All right. What I tried to say before timing the question is when you have this problem about mechanism, and you can use the picture like what gives you what you want to produce as in your mind as a guiding line. So always think about how can you produce the final product from the ether reactant. And then you see if each step is this, makes sense. Makes sense and use the usual common sense like positive, negative attracting, proton go on to those atoms like oxygen atom or nitrogen atom has long pairs, and those acid-base reaction and proton negative attraction like those. You go step by step, till finally you will get the product. So now one more last step, and now this time we will use the program is about produce the ether. So therefore we will keep this as plus, and we will keep this as C3. Now this time again we will use methanol, okay? But because there's a lot of methanol, right? So methanol will be our base, okay? And abstract the H. And then these two electrons from the OH bond, okay, go back to the alkene atom. And then finally produce our product. To make it easy to read, you just write out this series 3. And there's one side product, not that important, right? That's the one you will see you starting from. So that's kind of your acid catalyst. You recover your acid catalyst. And you know what is that, right? So at the beginning, I use 8 plus is our acid. Right? When we say acid is the catalyst, at the end, I change that to a little bit where I change that to the 8 plus, get onto the methanol. Right? It's very easy to write. At the beginning, this 8 plus, you can replace by this guy. Right? If you want to write it completely, where is your 8 plus? You just write 8 plus, you actually this one, right, is the conjugate acid of our methanol. So maybe I will write this up. Okay? So I will write this in parentheses. Okay? So this 8 plus actually same as this acid. Okay? So we write 8 plus sometimes just for simplicity. And obviously, if you add on this, down this side, you will also need to add on your side product. Right? You also need to add on this. Very good. Any question or comment? Now is our famous ether synthesis. Is Williamson ether synthesis. Okay? It's the best method for the preparation of the ethers. So what you use is a metal epoxide and a primary alkyl or metal halide or those torsylate. So halide and torsylate are very good leaving groupers. If you simply take the alcohol with your metal epoxide, then the OH in your alcohol is not a good leaving grouper. So sometimes you have to change that into a good leaving grouper by changing that into a halide, change your OH into a halide or torsylate. Now this torsylate is something like this. Now you compare those alkyl halide. Let's say use ethanol as one example. So you see this ethyl, let's say ethyl bromide. Ethyl bromide is those alkyl halide. And this reaction, this Williamson ether synthesis reaction, that means you will take some of those. Primary, then reacting with this, so this is one negative and one plus. And then, so the two reactants in the Williamson ether synthesis is these two types. So right now we talk about those air pure ethers, and then in chapter 21 we'll go back to study the ether again. We will talk about those aerial ethers. Aerial, that means so on this side you might have a bending ring, okay? On that side you have a bending ring. But right now you will see these will be the two rectangles, right? So the halogens it is identical, right? That means either PR or CS. Right? What is toxidates? So I saw that in the last example, example 1, some of you get a little confused. Right? Toxidates is like this. Right? So you will have this, ethyl. Right? Now here you will have this toxidate. So it's a very complicated structure. But you probably don't have to memorize the details, and you just memorize. So this part, if I change this part, this is our torsal. Torsal group is like this. You might have a torsal chloride, and so then the torsate. Torsate, you are including that O. That O usually initially comes from your alcohol. So torsate, or all those parts. So they have a torsate. So your torsate become very good leaving group. Torsate is good leaving group. So all those tedious work is pretty much just change your alcohol OH into a good leaving group, and then you can just perform those SN2 reactions very easier, or SN1 reactions. Right. So again, this is the best way to prepare the Williamson ether synthesis, and what you need is epoxide and those alkyl halide, or alkyl toxidate. And obviously you also want to know how you prepare the epoxide. Epoxide, for example, you can prepare that this reaction here. I get it from another book. If I use alcohol with some of those hydride, like sodium hydride, sodium hydride NaH is very strong. You have that H1 negative, it's a very strong base. Very strong base. Not very good nucleophile of that hydride from that NaH. If you want to use H1 negative, a good nucleophile, you will use those NaBH4, those H minus from that, or from that lithium aluminum hydride, LiAlH4, right? But it's a very strong base, so therefore it's attracting that H away and produces epoxide. Once you have epoxide, you can write your static ion like Na or platinum, or you can simply write the epoxide. Right? Instead of epoxide, which means you have some of those carbon group there, then you have this O oxygen has negative charge. And that is a very good nucleophile. You see the nucleophile, you have the table, the best one probably is sulfide, and then you have those thiols, then you can have those nitrogens, and alcohol oxide is a very good one too. So the electron from this epoxide and tag the carbon in alkyl halide and push that halogen out or toxidate out, and you produce your ether. Right? See an example. Make sure in this type of Williamson's ether synthesis, your alkyl halide should be methyl or primary. don't use that because this epoxide ion is not a strong base, and you will see those interactions. Four carbon, and one O, and one Na. Now we take our primary halide, and this time the halide is iodide. Is our S or iodide. Guess what it produces? So I think that's how we memorize those reactions, right? You have epoxide and halide. Williamson Ether synthesis. Right? So you produce the butyl ether ether. This name can call the butyl ether ether. Very good. Any questions or comments? There is a side product, so those inorganic side products, which means anything not that important. Usually, you don't have to worry about those side products. So what is important in this Williamson Ether synthesis is you make sure remember that. Okay? You try use those measure of the primary halide. Okay? So if I give some problem, like in this problem 16.7, okay? And I will give you a few of those ethers, and you identify what epoxide and what halide should you use. Right? The important line is you use a primary halide or the metal halide. You can break the bond, because ether have two of those bonds with two carbons. Right? You can break either one and say which one is your primary halide or metal halide. So what do you think about the first one? The first one, if I write those line structures, right? So I have ether, and I have this cyclohydrins, right? And if you cutting the bond between the oxygen and the carbons, right, you have these two possibilities. So which one shall we go? We can either use, let's say, this A, this B. The way A goes, that means you will use this, let's say we use bromide, ash of bromide, plus this. And so that's how the A goes. Okay? Now you go by the B, by cutting the line of B, right? So you will have this epoxide, negative charge here, right? Then plus, let's still use the bromide, like this. Okay? So according to what we said, you must use metal halide or primary halide. So therefore, the best way for this, for synthesis ether in A, we use what approach? The approach A, and the approach A. Not use this approach. What the reason not use this approach? Because it's secondary. It's a secondary halide. secondary the approach be, what you will get? So if I take this epoxide and plus cyclopentobromide, what are we expecting to produce? What is the competition reaction with our ether synthesis? If we use a secondary halide like this, this like cyclopentobromide. What is our competitive reaction? This is a strong base, right? And remember we studied those capital halide. We studied those SN1, SN2, always annoying. SN1, SN2, E1, E2. I think one line per one memorize, we have those halide, unless the metal halide, if you have a strong base, always think about that E2 first. A strong base always want to targeting the H plus. So the elimination reaction for the E2. So you will produce the ethanol, then produce the cyclopentene. Okay, now the second question, the problem is you want to produce this ether. And now let me draw the ether out. You want to produce ether, and then you want to produce this one. Similar, right? So what shall we use? Okay, now let me do it again. Okay, just this time. Cutting here. Let's see, cutting here, we call that the approach A. And that means you are going to use earlier, let's say use earlier, we use earlier bromide. I saw on the test, some of you also confused by this earlier and vinyl. So when you have this double bond, 3 carbon and 1 double bond, and this is the earlier. Right? So this earlier bromide, let's compare. So this is a vinyl or vinyl bromide. So I think that works the better way, right? So you take this and then plus your oxide like that. And that's it, right? That was the approach. You can write up like a forward way. The other way will not happen because the other way you will need a secondary halide. You don't write out explicitly. Okay? So you will write this O negative, and let's see the spectrum ion is sodium, then plus iron bromide, and we'll produce our product. Our product I switch the side of this ether. Okay? So I put the isopropyl on this side, but that's the same molecule. And then you cross NABR. Right. Now the last one. Okay. The last one, what you want to produce is this. What you want to produce. And let's see, I translate our molecular formula into this kind of line structures. And you will have just one carbon. I probably got too many carbon here. I need to bring it up. Right, so how can we produce this? Similar. Okay, so the best way is you will use our coordinate line here, and you will use primary halide and some of those alcohols. Okay, so here, and then let's see. Now let's write out this benzylic halide to a better. So 0 gram benzylic bromide. Yeah, so that's the way to do it. All right. Any questions? Okay, we'll finish this problem 16.8, and I will take a break. In the break, I will ask you to presenting your results for your quiz. Okay, now this problem 16.8. It's kind of review like what we studied in chapter 12. You want to produce this aerofil and aerial ethers. As I said, we are going to go back to study the aerial ethers more in more details, but here I give you a starting point. So let's say this, you want to produce this ether. Okay? So the ether you want to produce, let's say we have an X, then we have the bending ring. So we have the bending ring, and then we have this ether here, like this. Okay? Now you want to evaluate the possibility of both approach by either like use this is sulfide or the ethyl bromide. What the difference between this is X is CH3, or it will be the NO2 like this. Okay. Now the answer is you have two approach. You have two approach. It looks like you have this aerial bromide, or you have that primary bromide. If you want to use aerial bromide, it looks like a secondary or tertiary. Okay? So you usually will worry about the elimination reactions. Right? If you have a secondary aerogel halide, so if this bromine here is simply not on a bending ring, that's on a cyclohexane like this. If this is Br, then you have to really worry about the elimination. If you have the Br on the bending, you don't really have to worry about the elimination. Because the elimination will usually not happen because you have to break the aromaticity of the bending. But there's something other you have to worry, right? And Williamson's ether synthesis is actually an SN2 reaction. SN2 reaction, which means is nucleophilic substitution bimolecular. So you have to have the substrate available. So usually the bending ring will block your nucleophiles. So the reason it blocks the nucleophile because your bending ring has a lot of electrons on it. But if the egg is nitrogen, so as we study in the chapter 12. In chapter 12, remember we studied the so-called electrophilic aromatic substitution and the nucleophilic aromatic substitution. So it only can, for the nucleophilic aromatic substitution can only happen if you have some of those very strong electron withdrawing group on your bending. We know one strong electron withdrawing group is NO2, the other one is trifluoromethyl. So NO2 is electron withdrawing group. They're very strong. And also that CF3. So these two guys you probably want to memorize. If you have those on your bending, and then the ether you want to substitute it by something else is on the also or para position, then your nucleophilic substitution can happen. So the result after our analysis, use approach 1, you pretty much do an SN2 on a primary halide. Right? So then no matter what is your X here is methyl, or your X here is nitro. So the approach, as it run them out, so this is C3, and this is your bending. And let's see, you want to use this, this is called the P-methyl phenoxide. And this is negative, so this is plus, right? And you can react this with this bromide, ethyl bromide. What we will produce is this. So I still have this metal here, right? And then you have this O, right? And then you have this. Right? And we see this approach works. Right? So this approach, in our retrosynthetic analysis, is the top approach. And I just try to say, in your approach, you have that possibility X is metal and X is also nitro. Okay? So now let me just use some space, maybe the space on top, I agree something. Okay? And write out that the top approach use nitro on the para position. Okay? So we will have this N and O2. And our nitro on bending so this is negative, and then we have Na plus. So even though the nitro the nitro is electron withdrawing group here. It will take some electron away from the main ring. So therefore, we will take some electron away from the opposite, from this oxygen. Okay? But we still thinking you have enough electron left over on the oxygen. Okay? That can attack, go through the SN2 reaction. That can attack this primary halide. Okay? So you will have enough electron still left over on the oxygen, okay? And then attack this guy. Okay? You produce the same product, a similar product. You don't use that same because you have the nitro, not the metal. So here you have NO2. Right? So this reaction 1 here or reaction 2 here, both follow the approach on the top. Right? So both reactions we use the ethyl bromide. Ethyl bromide, the top approach. Use ethyl bromide, and then depend on what is your substituting on this bending, you might have methyl, you might have nitrogen.
But if we have the bromine as in the second approach, it wouldn't matter.
Very good.
Even though it's secondary?
Even though this is not really secondary because this is the article. This is the aromatic halogen. Right? So here it's not really, so this is different than this. If you have this, and no matter what is your X here, a methyl, a nitro, and the second approach will not happen. Well, then in the second approach to produce the ether, it will not happen. You see the pattern? Very good pattern. So if you have this secondary, this looks like a secondary. This bromide is not a secondary. Let me write somewhere. So this bromide here. So this is the aryl bromide, and here is the secondary bromide. Your aryl bromide halide compared with the secondary halide, there is a total difference. You usually will worry about this Williamson Ether synthesis. If you use a secondary with a strong base, you will see this E2 reactions. What is E2 reaction? E2 reaction means you take this away, you take the H away, you produce a double bond. Right? Now this aryl bromide, you don't have to worry about the elimination reaction. When you eliminate, you cannot eliminate anything here because you take this Br here, I mean, you take another H, you produce something that totally breaks the aromaticity. Right? So here you have an aryl. Aryl, which means aromatic. Aromatic is very stable. But if you think about you have to go to the second approach, which means you compare your approach, right? You compare your approach, you go backward. This is the vitro-synthetic. You go backward, you take this aryl bromide, and you produce this. Your aryl bromide have Br here, and here you have this kind of aryl ether. So every year you replace the whole Br by this isoxide. Then you recognize that happens, the name for that is actually nucleophilic aromatic substitution. Not elimination, okay? Not like addition. Right? So therefore, for the second approach, let's write out the second approach. The second approach, if you have this CH3 here, and you have this PR here, and then you use this epoxide. This is the second approach. This approach at the bottom, so I'm writing like a backward window, right? So I will take this brown painting. And brown painting depends on what brown painting, because these eggs can be CH3 or NO2. Right? You take this epoxide, right? And here written is sodium epoxide. You don't have to write the sodium, so you just write like something like this. Right? Now you want to take this to let this to a nucleophilic substitution. You have to attack this binding. So take a lot of electron here to try to attack on this carbon here on the binding. This one is called nucleophilic aromatic substitution. Okay. Well, what we study in chapter 12, this can only happen if this on the para or maybe on the also, and you have that two group. One group is NO2, the other one is the trifluoromethyl. If you don't have those very strong electron withdrawing group on your benzene, and this we see the possible. I will see the other word first. Possible nucleophilic aromatic substitution. And you have to evaluate this problem. You got to evaluate. So what can that happen or not? And we know this. Usually the aromatic compound, it can happen. We see that 5 reactant. It's sort of the electrophilic aromatic substitution. We can do a halogenation. We can do a nitration. We can do a sulfonation. We can do a Fred-Craft acetylation or Fred-Craft alkylation. And that 5 reactant in chapter 12 is about the electrophilic aromatic substitution. Alright? So nucleophilic, which means you have to have something that's relatively positive. How can you make your benzene ring positive enough and some of those nucleophiles can attack? And you have to add on your benzene ring with some of those electron withdrawing group, take some electron away from the benzene. Now benzene is a very, very unique structure. Depending on where you put your electron withdrawing group. So this approach, this reaction, no reaction. I can do that easy on my mind, right? Now let me take the other approach, this second approach, but with different binding. Right? So I will do an NO2 here, okay? And I will do a BR here, okay? And I will plus the O here, epoxide, the same name. Okay? So your now you can do a nucleophilic aromatic substitution. So we just abbreviate that as NAS. That will give us so what is the three way? What are the three way of prepare user? What is our first way we studied today? I give you the name so you can figure out. It's called the dehydration of alcohol. What is dehydration of alcohol? You take alcohol with alcohol and plus what? Huh? You can do the elimination of alcohol, right? But here you do the dehydration. So what you do, you will take alcohol with, take like 2 alcohol, maybe take 1 butanol, our example, and plus H2SO4 with some heat. That's the first way. Right? What our second way of make ether? Let me give you the name again. Called the electrophilic addition to the double bond or to the alkene. And what you use? I give you electrophilic addition to the double bond, which means one reactant is an alkene double bond. Right? The double bond plus what to produce ether? CH3OH, maybe, yeah, that's one particular example, which means alcohol. Right? So if you take a double bond with an alkene, plus water, you will see the hydration of double bond, you produce alcohol, a carbon-decoupled product. Right? Now, if you use acid with alcohol and not water, you will produce ether. Right? And a similar idea, a carbon-decoupled product. Right? Now the last method. What is our last method of prepare ether? This is the best way to prepare ether, but have some limitation, right? And you prepare ether, use a so-called Williamson ether synthesis. What do we use in the Williamson ether synthesis? We will use those either a tosylate, which means alkyl tosylate, or alkyl halide, and produce those alkoxide. You know what is alkoxide? Alkoxide, which means you have those alkyl group with O. Usually you will get that from alcohol, right? So the last way is alkoxide with some of those alkyl halide or the alkyl tosylate. Right. So then next, okay, we will come after the presentation of our phase. We will continue on this chapter. Okay? I think we want to do like more and more because we will see like in chapter 19, you need more time. Chapter 19 has a lot of chemical reactions. So if we have more time to finish this easy chapter, and then we will have more time to start this lengthy chapter. Similar idea. So let's see, we will have this time, and I'm going to start with group number 3. Okay? So group number 3 will be presenting the first pattern, then group number 4, 5, 6, 7, then we'll come back to group 1, 2. Okay, so group 3 will be the first pattern, group 4 will be the second pattern, group 5 will be the third, and group 6 will be the fourth. So these 4 groups come on first.
Why is that hard?
No, you do it. Your group You first show it and I will explain. So first write out the result.
So yours is right, it's just that you're supposed to go backwards. So start from there and then you go to there. Yeah, that's it. Because he says to use the back, so right.
Yesterday I forgot to take out.
So like,
So I brought it, like I'm having
to
here.
be honest,
But when I went to
reagents,
submit
I
it,
usually like to put those stuff.
Then
Usually city step. So like start with the product and then go to the intermediate and then go to like. Yours is right. Well, no, because these are the products, or the reactants, right? Yeah. So like these two would be in the same section. Like it'd be those two. So like it'd be like these two plus and these two plus. Yeah, it's like the thing. You did it. Yeah, that's how it is.
Show me the work. If I don't see your work, I will not accept your work. But I already posted an answer on the Higher, right?
One guy that
Not the most recent one. No. The one I just got, the one that was my How old were you when you were kids?
I'm not sure what.
Chapter 11.
What is it?
Chapter 11 back.
All just process, yeah. Oh, okay. So, oh, green or green reagents. So organic one. I'll try. I need help.
That's the base part.
Let's mix it up. Oh yeah. It's all you.
This is all you. Every problem is all you, Mr. 96.
How well did you do on the exam though?
Wait, we have to look on.
I think this guy was asking you to write out like the forward direction.
You need the forward reaction.
Yeah, I guess.
Yeah.
Like, how do you go? Like, I was freaking out. I was like, why is that one?
This with that. What does that mean? Oh wait.
That's a good idea. If you have a trend on one side, you put all of them in one part. Now you see it.
This is right. This is right because you're adding the order. No, I don't have a plastic. Yeah. So yeah, and then do they have like that right there?
I'm gonna say ranges and you're gonna say A, B, okay, F.
No, I didn't feel it. I'm not actually.
I got it.
No, I can. You get a 30, you get a 30.
Oh, okay. I didn't feel it.
No, that's no proof against 30.
Yeah, I'm happy with it. Like, so you like ended it.
Why you always have €1 euros? I don't know, man. I think I can get on the table.
Oh, you were half point. Oh, yeah, I'll go back.
62.5, not percent. We're talking
I know, yeah.
It's really not.
You know what, you'll get the next one, okay?
Well, it's not on.
No, I just see chapter 15 next year.
Yeah, there's a lot next year.
Yeah, I'm content with that. I'm like, it's steady. No, I mean, I'm like, I'm shooting for 100%, I mean.
45 since the beginning. I'm not at a 6.
Wait, 745, what's that? 5 points. That's 5 points.
Yeah. Which I guess maybe, I'm guessing that means like that's what yeah. That would make sense. Yeah.
So you're like,
Yeah, that's with the drop.
You got my back, right? No, a C. It's 25.
These are also guys.
No, only on COD standard.
that's how it works.
I know, right? I'm not your fault right now. Hey, you know it's not you, we'll pass the grade.
Okay, now let's do every group of presenting your result for your quiz. I said we start with group of 3, right? So group of 3 is 1, then we'll go on until group of 8. Then we'll come back to group of 1, group of 2. And all the questions, 3, 4, 5, 6, okay, we missed 7 and 8. And 7 and 8, so I need group of 1 to 7.
It went 3, 4, 5, 6. Yes.
I'm actually doing research.
Alright, now let's first see this. I will see the explanation for this first 6 pattern first. We have 8 pattern, right? Okay. Who is I think Nadia, right? Patel, right? You did the pattern number 1?
No, we did 6.
You did 6. Who did the pattern? Yeah. Okay. Tony and Tammy, you explain the pattern number. Pattern 1. Yeah, maybe I can make it better to record.
Okay, question number 1, we have a double bond here on the oxygen that can be broken by the Grignard reagent. This comes in here, attacks at this point, which bounces it out over here, picks up an extra hydrogen from the acid we have here, and that permeates it, thus leaving us with an alcohol on the ring and our methyl.
Okay, good. So this reaction is about bringing out this ketone, right, as you said. That is a tertiary alcohol.
That would be the nicest way to put it, yes. I didn't have the words.
Okay. Well, that's the only pattern you did?
That's the question we did.
What do you do, like also the pattern number 7? I think we don't have pattern number 7, right?
Nobody did 7?
Nobody did 7 yet. So probably you can do the 7. Maybe do the 7 over there, and that means 9 come back, will come back there to this 10. So who did number 6? You did it, right? Okay. I think Patel and you, so let's explain the number 6. Come forward.
Okay, so on the reactant side, we have the cyclohexene plus CH4, and that will react to KOH, which for the product side, we go these two will kind of match with Cl weighted and these arrows is right. This is coming forward, the dot line like shows it.
Good. So that means you produce the cyclic 3-member, adding a 3-member cyclic partner on the middle LG.
Yeah.
And then you add on the same side. So therefore you have that 2H on one side. And in addition to that, the 2Cl also like the tetrahedral geometry. Yeah. Very good. I think this pattern is related to the pattern we see in number that writing in red over there, right? So those patterns is about so-called carbines. Related to the carbines, not real carbines. Carbines like the fiber H2C long pairs. So they were adding on to those carbons, double bonds, and produce cyclopropane, 3-member ring. Okay. I hope in this way you will memorize a little better, and study group is very important, interesting. So talk to each other, study together. All right, number 5. Who did number 5?
Okay, well, this was a retrosynthetic problem. So we're trying to go from this as our product and break it down and go backwards. So we found out that we could break this bond right here, and it will have this plus charge right here, and then the methyl and ethyl group on the side. So from going there, we added this bromine using this lithium cuprate. Is that? Yeah. Yes, with the diethyl ether. And what that does is bromines
pure reagent. The organocuprate, or the lithium dimetal cuprate. Very good. All right. So the next question is the one in red. Which group is the one in red?
So number 2 is for identify the missing components of the following Simmons-Smith reaction. So when you use the Simmons-Smith reaction, it creates a cyclopropane, and in this situation, because we're using Z3-hexene, which Z is just for the isomer, it changes to a cis, just due to the fact that we're using Simmons-Smith reaction, which has the reagents of CHF2, I2, and zinc, copper solution type.
What's your name?
Oh, Gabe Williams.
Gary
Yeah,
Williams.
Gabe.
Williams is Ether synthesis.
Oh, yeah.
Oh, very good.
I've heard that one before.
Okay. Gabe, and what's your name?
Shane.
Shane, and your role? Very good. I think Gabe specified what is your reagent, what is interesting also the stereospecific property for this drugs. So if you start with cis alkenes and your 2 esters on the cyclopropane is also cis. What about if you have a trans alkene? If you have a trans, these two. Yeah, if at the beginning you have a trans, as you have a trans of the. This is Z, right?
Yes.
What about if E3-hexene?
So if it was E3-hexene, then you would have, I think, a trans at the end for cyclopropane.
Right, right. All right. Well, were you guys, Shane and Gabe, were you guys also do the number 8? Right? Let's do the number 8 over there. Do the number 8 over there. Okay, so next question, what is this number 4? Who is number 4? Kyle, what's your name? Yasser. Yasser, yeah. Yasser, Kyle. And what's your name? Aditi. And Avi.
Okay, so the question has to develop the synthesis for 2-phenyl-2-butanol right here from benzene and 2-butyne. So you would brominate the benzene, then you would use the Grignard reagent to get a MGBr on the benzene, and then you would use an acid catalysis to get a double bonded O, and then you would use alcohol synthesis. So then you would use alcohol synthesis on these 2 reactants and get 2-phenyl-2-butanol, and then that's the retrosynthetic reaction.
All right. Any questions? So you use a green yarn?
Yeah.
Okay. The power one here you use a green yarn, right? Okay. What else you can use if you don't use green yarn? If you still will take, let's say the. Very good. Okay, no, you can. Yeah. Anybody see my question? So here you use the green yarn, right? Green yarn is a magnesium with some of those bromine, right? And so Yasser said, right? Yasser? And you can also use the organolithium, right? So the second reaction you need is that 2-butanol, right? So this is 2-butanol. And here you produce from this 2-butyne, right? you use hydration of H2O and sulfuric acid and mercury sulfate. What else can you use instead of that mercury sulfate and H2SO4 and water? Okay, 2 steps, and for this reaction, you pretty much get the same result. What is the other way? So here we can do like a straightforward. We use hydrogen, and we use mercury 2 catalyst, and we also use H2SO4. Right? There's another way of hydrogen called kind of with boron. Anybody remember the name? You have to use boron, which is B. And hydro. The same way you say hydroboration oxidation. There is a little difference between the hydroboration oxidation and hydrogen. If you have the terminal triple bond, right? If you have a terminal triple bond, with this method, and you will produce this is terminal. Well, this is not a terminal, right? So this is not a terminal. With a terminal, I hear somebody say probably recognize, but this is not a terminal alkene, right? With a terminal alkene, you will have the 2 difference. So this is not a terminal, right? With a terminal, for example, you have something like this. And then you will have a choice. With this approach, you will produce this. So this is H2, and then some of those acid, and then He2+. So produce the methyl ketone. If you use B2H6, your first step, the second step is like H2O2, adding some of the base. And what you produce is this. See the difference? Right? So hydroboration oxidation, you produce aldehyde, and good straightforward hydrogen, you produce a methyl ketone. Just anyhow, you probably sometime will see the little difference. Any questions? Okay, thank you. You're pretty good. Doing radiosynthetic, then you just do the forward way. Alright, and let us see the next one is number 7. Who did number 7? Number 7, you did number 7, right? So Tony and Tammy.
This one, we've got a line over here, the sodium would dissociate, leaving us with a nucleophile over here on the carbon, which would attack at our double bond over here, sending the extra electrons up to the top of the oxygen.
That's right, use the arrow.
I can't draw it, I'm sorry, I'm too short. Wait. And then the electrons bounce up to the top.
Right.
All right, at this point, it grabs the extra electrons up there, grab a hydrogen off of the acid, making that a water.
Work out.
So what is that, guys? Tertiary alcohol? Tertiary alcohol.
Yep. to get on the oxygen. I think it's yes, there's some of those basically you have to be even size to get those right. All right, any question for them? So what do we have? Andy, Tammy, and Tommy, and Andy. All right. Thank you, that's good. All right, now go around to three, number three. What's number three? Another zero max, right? Okay, go ahead.
Okay, so essentially for number 3, we're given these two reactants and asked about the product. So what occurred was a Grignard reaction with the lithium, which removed the bromide and added carbon. What?
Zero max.
Yeah, that's what I meant.
Yeah.
She's confused.
All right. So what is our reactant? Is this the human reactant, right? The lithium diacylate. The other one is a kind of wine or bromide. You keep the stereochemistry there, right? If you have a trans there, you will have a trans product. Get that? So you double bond the trans, and you can still have a trans. Right? So what is this? What is this one?
This is not ours.
That's
Not yours? Okay, now see what here? What's your name? Unica? Critica.
Zishan.
Zishan?
Yeah.
John? Jesse. All right. Good, thank you. Is this a different pattern? This is the pattern number 4, right? This is pattern number 4, yeah, this is that. All right, so what pattern we need not do yet? 8, that's the only one? 8, Maria, what's your name? Christina. Justina said, right? Justina said. Okay, just a minute.
Okay. So we have number 8, we actually start from benzene. So we use Br2 in the catalyst to add the bromine. And then this is the general reaction for the Grignard reagent, this one right at the bottom. And then we use an organic halide with magnesium using diethyl ether.
Okay, produce the Grignard.
Yes, using Grignard.
Okay.
And then we got the organo-magnesium halide, which is phenol-magnesium bromide. That's the result, but
That's
like a general reaction.
That's the name.
Yeah.
And call it the phenol magnesium bromide. Okay. That's the one. That's the pattern.
Yeah, that's.
So then what you can use with the Grignard to do something like produce alcohol or something, right? Grignard. See one reaction. Find one reaction that we use Grignard. Are there any reaction that we use Grignard like on this board? There is one. Yeah. Where's our magnesium chloride? And what do you use there? What do we use the Grignard in question 1? Yeah, what do we
Right there.
produce a church?
Yeah, to an alcohol.
Yeah. Right. So you can use that on ketone, right? Use that on the aldehyde, produce the alcohol. So that is what kind of alcohol? Tertiary? What do you use if you want to produce a secondary? Still use Grignard. See my question? If you still want to use Grignard and you want to produce a secondary alcohol, so what do you use? Very good. Normal aldehyde, right? Like the acetaldehyde. what if you want to produce a primary alcohol? Use thinner, right? But we are doing better on the you have one. You need to look how you have one. I think that's it. What's time now? Over 8.
Tomorrow, and then we don't wait 6 till,
Yeah, you think a 50 at home, I put an article about this, holding quiz on the I did not put study a little bit. I put the answer on here and quick, just quick. I'm supposed to be with the camera 15. Right now, can you go to my office? I will right now. If you want how much you will get
It's like I have to tomorrow. I have to listen to the 7 out. The one that, that's that product. Well, you have to like give you like the seed of the market and figure out the structure. You should do that because I feel like when I oh yeah. Stressful. Every morning I want to go to. I feel like it's but tomorrow you ask oh, sorry, not last Saturday. I think one today it was there's only one. Yeah. But it was unusual. It's like
you have the what? Can you do them today?
You'll play something like, oh, I want to get one